Hello students, welcome back. Let us resume our discussion in section 1. Previously, we went through the definition of the congruence. A and B are congruent modulo M means the difference A minus B is a multiple of M. Left-hand side minus right-hand side is some integer times M. That's the definition. Under this definition, we proved an important property of the congruence. Two integers are congruent modulo M means they share the same remainder when divided by M. We proved another property, the equivalence property. The congruence is actually an equivalence relation. Now, if you are really comfortable with the theory of equivalence relation, then from here you will be able to set up the equivalence partition and the quotient set, and then we can induce the algebraic operations. And the original set is C, the set of all integers, equipped with the addition and multiplication, and the quotient set will have induced addition and induced multiplication, and so on and so forth. Well, that's nice, but that's a bit too advanced. We do that in abstract algebra, 4000 level, but this is 3000 level number theory, not 4000 level abstract algebra. So let's take a little bit easier path. Instead of defining modular arithmetic as new algebraic operations on the quotient set, we'll just use the usual addition and multiplication in Z, the set of all integers. So these are both integer operations. Instead, we prove that both are preserved, both addition and multiplication are preserved under this congruence modulo M for all positive integer M. That's what we are going to prove. Let M be a positive integer, and we just define M, so it's arbitrary. So for any positive integer M, if A and B are congruent and C and D are congruent, then addition, A plus C and B plus D are congruent, and multiplication, A times C and B times D are congruent, all modulo M. That's what you have to prove. Now, how can I rewrite those using the definition of the congruence? Left-hand side minus right-hand side is some integer times M, right? So we can rewrite the left-hand side like this. A minus B is some integer times M, and C minus D is some integer times M. That's the left-hand side. And then the right-hand side, well, the definition is this. Left-hand side minus right-hand side is an integer times M. So let's go ahead and do that. Left-hand side, A plus C, minus right-hand side, B plus D, is some integer times M. That's what we have to prove. And then we can prove the same thing for multiplication. So under the same condition, instead of A plus C, we have A times C. In place of B plus D, we have B times D, and we have some integer times M. And basically, we are looking for these integers. One more comment before starting the proof. One very common mistake I see is using the same character used here in the definition. Here in the definition, I use K. So use K here. So far, so good. Use K here again. Now that's not good. Each time you use the existential quantifier, you have to bring in a new character, because there's no reason these two have to be always the same. They may be same sometimes, but in some other cases they may be different. So you can use two different notation like K1 and K2. Or as I did before, I and J. I started with I and J, so let's stick to those. And you can use whatever characters as long as they are not already selected. And then if I and J exist, then it turns out this integer will be an expression of I and j, so this integer exists. Same here. This integer will turn out to be an expression of I and j, so that if I and j exist, then this integer exists. That's the aim. And let's go ahead and prove it. All right. So condition can be rewritten as IM and JM like this. And conclusion that we want to prove is A plus C minus B plus D is an integer times M. Now, how can I manipulate the left-hand side so that you can use A minus B and C minus D? Well, stop the playback and try on your own. Got it done? I can change the order of operation like this. Let's put some space in between. So, A minus B, C minus D. If I distribute these negatives, they are both negative. And then A minus B is IM, and C minus D is JM. So I can factor M out, and what's left is an integer. So you see we have M times integer, and that's precisely what we wanted to prove. This completes the proof. See, we have that. Consequently, these two are congruent. So that completed the proof for addition. Now, would you like to try the multiplication? Would you like to stop the playback and try on your own? Go ahead. Well, time is up. All right. So that's what you want, right? A minus B, C minus D, IM and JM. Yeah, same condition. By definition, can be reduced like this. And then the conclusion here can be rewritten as AC minus BD. The left-hand side minus right-hand side is an integer times M. How would you do this one? Got it? We use a very typical trick that we used before, as a matter of fact, and when we prove the transitivity of the equivalence property, the third one, I hope you guys remember, we can add and subtract the same thing. So AC minus BC plus BC minus BD. So the net change is 0 because I added and subtracted the same thing. But then again, if I do it this way, first two terms have C in common. So factoring it out, we have this. And then the second two terms have B in common. So factoring B out, I get this. Does it help? Oh, yes, it does. A minus B is IM, so this is IMC. And then C minus D is JM, so BJM. M is common, so I can factor it out. And what do I have here? IC plus BJ. And do we have M times integer form? Yes, indeed. That completes the proof. This is an expression of I and j. So if I and j exist, then this integer exists. Yeah, everything works out. Add and subtract the same thing, and then manipulate like this. Does it look good? All good? Okay, we proved it. Now let's do some applications. Here's an example. Evaluate this expression, 3 to the 5th power minus 4 to the 7th power times 4 to the 8th power modulo 9. And then the same thing modulo 6. I have a feeling we have two different answers. We'll have time for only one of them, so let's go ahead and do this. So we want to do this computation, right? All right, this computation. So 3 to the 5th power times 4 to the 7th power times 7 to the 8th power is congruent to what? Let's do this computation. 3 to the 5th power. How about that computation? Well, 3 times 3 is 9, and 9 is congruent to 0. So this is pretty simple. 3 squared is 9, so that's 0. So 3 to the 5th power is 3 squared times something, so it's 0 times something, so 3 to the 5th power is 0. So what do you have here? Let me copy and paste this entire thing. This turns out to be 0. Okay, 1 down, 2 more to go. Next, 4 to the 7th power. Okay, this needs a bit of work. So we want 4 to the 7th power, 4 to the 2nd power, how about that? That's 16, and that's 7 modulo 9, but it's going to be a bit more convenient if the size is smaller. So let's go to -2. 18 minus 2, so -2, and it'll help in the next computation. 4 to the 4th power is -2 to the 2nd power. Oh, by the way, this should be congruence. And that's 4. So 4 to the 4th power is 4. Alright, so 4 to the 7th power is 4 to the 4th power times 4 to the 3rd power, 2nd power times 4. So 4 to the 4th power is 4, and 4 to the 2nd power is -2, and 4 again. So what do you have? 4 to the 4th power is -2, and then another -2. Okay, I'm gonna get +4. Actually, this, if you want, you can use everything is congruence. Yeah, just sometimes using equality, sometimes using congruence. If that's confusing, just use congruence for everything. But to be really precise, this is equality, and that too is equality, and we use congruence here and there. Anyway, it's 4. Did I do this right? Oh, conclusion is right, but I like this computation better. 4 to the 7th power is 4th power times 4 to the 3rd power. So 4 times 4 to the 3rd power, so it's 4th power again, back to 4. Yeah, it's simpler than this one. I like this better. 4 times 7th power is 4th power times 3rd power. And 4th power is just the same, it's just 4, so 5th power. So we're back to the 4th power, and which is just 4. Alright, so this is just 4. Okay, alright, 2 down, 1 more to go, and then let's do 7 to the 8th power. Let's see, what is 7 to the 8th power? As a matter of fact, let's start from 7. 7 is congruent to -2, modulo 9, and reducing the power is more helpful, you see. So 7 to the 8th power is -2 to the 8th power. So -2 to the 2nd power to the 4th power. -2 to the 2nd power. -2 times -2 is 4, right? So it's 4 to the 4th power, but then again, we saw that that's 4 in the previous part. So this entire thing is 4, according to this computation. Let's see, what do you have here? Yep. 7 is -2, congruent to -2, modulo 9. So 7 squared is -2 squared, so 4. So 7 squared to the 4th power, 4 to the 4th power, that's 4. So what do you have? -16. But then again, that's negative of -2. So it should be 2. Yeah, it should be 2. So we can do this modular arithmetic freely with all kind of addition and multiplication repeatedly.